So this is for college physics 2, physics 124, unit 2.1, waves and sound. I'm going to do some of the openstax problems, not all of them. So here we go. It's the first one I'm going to do. Fish are hung on a spring scale. This is from chapter 16, number 1. Chapter 16 is called Oscillatory Motion and Waves. So it's a fish problem. Fish are hung on a spring scale to determine their mass. Okay, most fishermen and so on. What is the force constant of the spring of such a scale, in such a scale, if the spring stretches for this much load? What is the mass of a fish that stretches the spring this much, and how far apart are the half-kilogram marks on the scale? Okay, so let's get started. So here you have to envision a spring that is holding a load, and as it's holding a load, Newton's second law applies to that. And then I already hit some text here, so I'm going to turn this back on. And so the sum of the forces on that load that is hanging there is then the weight, and then the restoring force, which is Hooke's force. And then because the whole thing is supposed to be in equilibrium, that's why we see a 0 there. Okay, again, I've already prepared a little bit of text here. Oops, and then I didn't highlight enough. So try it again. There we go, there we go. Okay, now it gets a little interesting. The weight here, of course, is negative mass times gravity, because the weight is pointing down. Okay, then this part is interesting. Hooke's law is also negative k times the distance by which the spring stretches. But the thing is, the distance itself is negative as well, which means this total thing here is positive, or overall, we actually have 3 negatives in here. So we'll see what happens with that. I'm going to do some algebra. We're supposed to figure out in part A what the spring constant is. So I already wrote down the spring constant K here. That means I'm going to get the negative mg to the other side, which is going to make that positive right there, m times g. Then I have to divide by x, so there's the x. And then I divide or multiply by that negative, and I had already written that negative. There we go. So we get rid of that one of those negatives, this one over here, by putting it to the other side. That one here actually stays alive. And then remember that the x here actually will be negative in a moment. So I'm going to pause here for a moment. All right, so I'm going to plug in the numbers that are given. So this is the 10.0 kilograms times, and now I wish I had prepared that. All right, I found it, the times. So 10 times, and then gravity, of course, is 9.80. And on here, I'm going to divide by the 8.00 centimeters, but it needs to be in meters, so it's going to be 0.0800, you know, the sig fig meters. And put the negative in front of it, because the spring stretches downwards, so there's the negative. That's a third negative. The first one is already gone, and then these two negatives actually divide out. And here I'm going to have a plus. The number I'm going to come up with is 1,230. And the units that I'm going to have here, this one here is mass times gravity, which is newtons. Divide by the meters here, and that's actually also how it's written. So this one is going to be Newton. Divide by meters, which is the unit for the spring constant. By the way, I did find a photo for that. So this would be here at a fish market in the Philippines, and the spring actually would be in the meter here, and she is actually weighing fish. All right, going to get a little pause here to do the second part. All right, second part, turns out actually same equation, and then plugging in the same things, and here again. And then this time around, though, solving for the mass. So I get the kx to the other side. So here's k times x, spring constant times the stretch x, which again will be negative. Divide by g, because I got this here to the other side. That's why this part here is positive, that part right there in the numerator. And then I divide or multiply by a negative, so that's why there's a negative in the front. Okay, I'm going to plug in the numbers. So this one is 1,230, or before I round it, it's 1,225. Multiply by, and this one is given as, and again I have to put a negative in front of that, so negative 0.0550. Again, it's a negative because the spring stretches downward, and then divide by the 9.80, and when you do that, come up with 6.875, respectively 6.88 rounded, which itself is an overkill. 6.97 kilograms. Oh, by the way, the mass should be kilograms, right? So here we have newtons. When you divide newtons by an acceleration, by definition, you come up with kilograms. So it is 3 sig figs, so I'm just going to leave it as 6.88. But again, it's just a little bit too accurate. The fish is 6.9 kilograms or 7 kilograms. All right, again, take another pause for the third part. All right, so for the third part, again, do the same thing. Newton's second law applies. Weight equals the restoring force from Hooke's law. And then we have negative mg minus kx equals 0, just like before. And it turns out that this particular problem, you're going to solve for everything in there at least once, or exactly once, except for gravity itself. So anyway, so here's the distance by which it would stretch. And let's see, I'm going to get the mg to the other side. That gets rid of the negative, but then I have to multiply with this negative, or divide by it. That's the one in the front here. And then I'm going to divide by k. So there we go. And now I'm going to plug in the numbers. And let's see, mg, oh yeah, that says 0.5 kilograms right there. And a half kilograms mark on the scale, and they don't say that it's any more accurate than that, but all right. Times 9.80, divide by the k, 1225. Notice this time we don't have a third negative, so the negative actually survives. And when we plug that in, 0.5 times 9.8, divide by 1225, and I come up with 0.004, which is newtons divided by meter. So newtons divide out, and the meters goes to the top, which makes sense because I'm supposed to come up with a distance. So 0.004 meters, or if I want to put it into something more that we can better look at, 4 millimeters. The negative makes sense here because it's stretching down. The 4 millimeters is really small for the half kilogram, so it doesn't stretch much for half a kilogram already, and that's why I'm saying that the significant figures for the previous result, the 6.88 kilograms, are just too accurate in there. That's why I said, 6.9 or 7 kilograms, because the stretch of 4 millimeters for already half a kilogram is quite a bit. This is actually a pretty robust spring scale that is being used here. All right, make a pause before I start the next problem that I want to do. All right, the next problem is about the Cuckoo Clock, and here I found an image. I think we can see that. Appears to be a German invention, and because cuckoo is a tough word to pronounce, I will use the German pronunciation. I will call it a Kuckucksuhr. Uhr meaning clock. So a type of Kuckucksuhr keeps time by having a mass bouncing on a spring, usually something cute like a cherub. In a chair, what force constant is needed to produce this much period for this much mass? So what I'm going to use for this one is the equation for a spring, for the oscillations of a spring, how much time it takes for one oscillation looks really similar for as compared to the oscillations for a pendulum, except in a pendulum in this equation you would have replaced the m over k by L over g. But in any case, yeah, the two are really close to each other. And then since I'm supposed to figure out what the spring constant is, force constant, spring constant, same thing. So turns out, just like the problem that I did previously, figure out the spring constant. So I have to solve for that little k down there, which means I am going to square the t. So I'm going to square the t, so I'm going to have t squared. I'm also going to square the 2 pi, which means I'm going to have 4 pi squared. And then the m is just going to be by itself after I get rid of the square root. And the k is also going to be by itself, but it's going to go to the left-hand side. So I multiply by the k, and I did that here, which means on the right-hand side, stuff is going to stay the same, except this one is going to be a 4 pi squared. So I'm going to put that in here, 4, and then I'm going to put a pi there, and then I have to find my pi, which is, when you type, is really cumbersome. There we go, I got it. 4 pi squared times the m that you see there. I'm gonna try to get back into the numerator. There's the m. And then once I got the k right here to the left-hand side, I had to multiply with it. Well, I have to get rid of the t, which means I have to divide by it on both sides. So that's why the t squared will end up right here. And I think you kind of see how I prepped that. Okay, so here I got, let's see, I'm just gonna try to copy the 4 pi squared right there. Let's see if this works. There we go, and put in the values 0.0150, and then divide by the time 0.500 squared. And I could have prepped that too, I guess. So here's my calculator: 4 pi squared times 0.015 divided by 0.5 squared, enter, and I'm going to come up with, or round it, 2.37. And let's see, the units are kilograms divided by seconds squared. I realize that. Kilograms divided by seconds squared looks really weird, but if I do this, watch, I'm going to put a times meter, multiply by meters. At the same time, I also divide by meters. So kind of like this here. There we go. So I multiplied by this meter and I divided by this meter here. Why did I do that? Well, because it's a spring constant and kilograms per second squared is really strange. So as I multiply by meters, I get this, kilograms meters per second squared, which is newtons. And then I have the meters down here that I had to divide by after I multiplied with the meters. So I'm going to have newtons divided by meters, which is the unit for the spring constant. So it was just a roundabout way to get the unit there. Okay, I'm going to pause. All right, the next problem I'm going to do, so engineering application here near the top of the Citigroup Center building in New York City. There's an object with mass. This one is a whopping 400,000 kilograms. So a mass of 400,000 kilograms, almost 1 million pounds, on springs that have adjustable force constant. Its function is to dampen wind-driven oscillations of the building by oscillating at the same frequency as the building is being driven. The driving force is transferred to the object, which oscillates instead of the entire building. What effective force constant or spring constant should the springs have to make the object oscillate with a period of 2 seconds? What energy is stored in springs for 2 meter displacement from equilibrium? Wow, that's a lot. 2 meters, 500,000 kilograms. So I found this one here, the tuned mass damper, and that's basically what it is. This one here talks about the Taipei 101, so another huge skyscraper, and then here would be kind of the mechanism for the springs, and then this one here would be kind of like a damping curve, respectively, these here as well, so that the the building stops swaying, or at least gets down in amplitude. And apparently mass dampers in automobiles, you're familiar with them, the suspension that we have, and they're just placed here in the tower here itself. I don't know if they use springs on this particular one, but some kind of mechanism. Earthquakes as well here. So anyway, examples of buildings. Oh, let's see if they have United States here. Oh, there it is, Citigroup Center in New York City. And it was one of the first skyscrapers to use a tuned mass damper to reduce sway. It uses a concrete version. There we go. It's right there. If I click on that, maybe it's even in here somewhere that they talk about that. All right. Okay. Anyway, so let's get back to the problem. Yet another problem where I'm supposed to figure out or you're supposed to figure out what the spring constant is. So here we go. It turns out it's the same equation and it's the same algebra. So I'm not going to do that again. You just saw me do that. I'm basically just going to plug in the numbers there. So the mass here, that is that whopping 400,000. There we go. And then this one down here is the 2.00. And when I do that, I'm going to come up with, let's see, 400,000 divided by 2 squared into 4 pi squared. And I come up with, let's see, 3.95 million. I'm not going to go to the extent of trying to figure out scientific notation here while I'm typing. And this actually would be easier if I was able to write, but it so turns out that I can either write on another computer and use Zoom to record this, or I'm here on my own computer, but now I'm going to use another software to record this one here, Camtasia, but I don't have the luxury of writing, because writing would be actually a little nicer than typing. Typing is a little cumbersome with equations. Okay, anyway, there's a spring constant here, and then I'm going to make a pause for the second part to prep that. All right, I'm ready for the second part here. So what energy is stored in the springs for this 2 meter displacement from equilibrium? This is the equation that you will find for the elastic potential energy. It looks like kinetic energy, 1/2 mass velocity squared. So this elastic potential energy is 1/2 times spring constant times the displacement squared. When I typed in the PEEL, it actually suggested peel, but oh well. Like I said, anyway, 1/2 times, and then I'm going to have that 3,950,000 right there times the 2.00 squared. So when I do that one here, so times 2 squared, and then divide by the 2 in the front, I basically actually double that, multiply by 4, divide by 2. And so I'm going to come up with a rounded 7.90, yeah. So 7,900,000, oh, what did I say? Yeah, actually, yes, yeah, rounded, 900,000. And now that would be joules. That would be that, let's see, the K here is Newton per meters. Then this one here is meters squared. So that means Newton per meter times another meter. Get rid of that, so it's simply Newton, but then the meter was actually squared. So multiply by another meter. So technically this is Newton meters, which indeed is the unit for work, but that of course then is also the same as joules from the energy and work chapter. So there it is. And really no comment on that energy. I assume that's just quite some energy in there. Again, pause. All right, almost the next problem. So I did look at the Wikipedia article for the Citicorp Center, and so here it is. Was the city's first skyscraper to feature a tuned mass damper. located within the rooftop mechanical space, and so on. There's the 400 short tons, which is 400,000 kilograms, or 800,000 pounds, or a little bit more. I would have to look at what's the difference between a long and a short ton. I kind of know, like one of them I think takes on a conversion of 1 to 2 between kilograms and the pound mass, and the other one takes on the 1 to 2.205 between a kilogram and the pound mass. Anyway, I think that's the difference between the two. So that concrete block is 30 by 30 by 6 feet. That's pretty big. 9 meters. That's a couple, 3 stories, you know. Yeah, and it sits in a pool of oil within a steel plate and has 2 spring mechanisms that counteract each other, and it costs $1 million to install, and so on. All right. Okay, next problem. So ocean ripples. Wind gusts create ripples on the ocean that have a wavelength of 5 centimeters and propagate at 2 meters per second. What is the frequency? So this is the equation: velocity or wave velocity equals I'm going to start over. Wave velocity equals frequency times the wavelength lambda. In the book called pretty much everything the wave velocity, I make an exception for the speed of sound, which I actually will call VSOS, speed of sound, velocity of the sound, right? So anyway, it wants to figure out the frequency, so I do one algebra step, which is F equals that wave velocity divided by the wavelength, and the wave velocity is given as 2.00, and the wavelength is given as 0.0500 meters. So I had to convert that from centimeters to meters. I can do that in my head. That ought to be 40, right? I would think. Yep, it is 40, and I guess with 2 significant figures, it's actually 40.0. This will be meters per second divided by meters, which means the meters divide out, and it's per second. And per second, for that, we use the hertz as unit. So the frequency is 40 hertz, which means you get 40 ripples in a second going by. All right, this is the next one that I'm going to do. I guess I call it the spear scream. When poked by a spear, an operatic soprano lets out a 1200 hertz shriek. What is its wavelength if the speed of sound is 345 meters per second? I guess, why would he or she, I think a soprano is a woman, be poked by a spear? Maybe an accident or something. The closest I got was that there's a scene in Richard Wagner's Parsifal where that actually happens. This is the German Wikipedia site, so I'm going to go back to the English one because that actually has a depiction of where that happens. Right there it is. So I guess there you go, and then I guess it hurts and you let out a shriek. Okay. So same equation, wave velocity equals frequency times wavelength lambda, and again this time, or like I said before, this time I actually call it VSOS, speed of sound, just to distinguish it from the other wave velocities. And that also comes in kind of handy when I do Doppler, if I do Doppler effect problems, the SOS just comes in a little bit more handy. Okay, anyway, in this case here, they actually want to figure out the wavelength lambda, so I solve for that. So hence lambda equals VSOS divided by F. I'm going to plug these in, so it's going to be 345 meters per second divided by the 1200 hertz. And let's see, 2 or 3 sig fig. I'm tending towards 2 sig fig because of 1200 hertz. So 345 divided by 1200, there we go. 0.29. There we go, 0.29. And then it's going to be meters per second divided by hertz. Well, the hertz is per 1 second, which means the per 1 second actually divides out and at least meters behind. So the wavelength of that is 0.29 meters. All right, so next problem here. What sound intensity level in decibels is produced by earphones that create an intensity of 4 times 10 to the negative 2 watt per square meter? So I'm going to use the equation for the sound intensity level. So beta equals 10 times the 10 log of the intensity over the threshold intensity. I already have this prepped, as you can see, so 10 times log. Here's that 4 10 to the negative 2. This time I really cannot avoid scientific notation. I'm going to put the threshold intensity in here, which is 1 times 10 to the negative 12. And that one is defined as a reference intensity, and this is from the book directly. In particular, I0 is the lowest or threshold intensity of sound a person with normal hearing can perceive at a frequency of 1000 hertz. So kind of like the threshold intensity. So a very small amount of energy per second per square meter that a person can perceive. So that's what I'm going to plug in. The units, by the way, when I plug these in, are watts per square meters for both the numerator and the denominator, which means they all divide out these units. I take the logarithm of that, which still divides out, which still means that there are no units that are multiplied by 10, and then we're actually gonna simply attach the name decibel to it, keeping in mind that the decibel actually is a logarithmic unit. All right, so I'm gonna do this one here. Let's see. 10 times the log of parentheses 0.004. I did that without sig fig, and then divide by 1, and then e negative 12. I hope this works out. Parentheses, or enter 96. I have 3 sig fig, so I guess it's 96.0 decibels. Okay, I actually had to pause myself because I was looking at that 96 decibels that I came up with compared it to the solution manual, which said 106 decibels. And then you might hear me say that I took the log of 0.004, which is incorrect. It's the log of 0.04 with that negative 2 right there. And now I get the correct result, actually, of 106 decibels. So yeah, I actually had to pause a little bit. Unit is decibels there, because it was a little off there from the solution menu. Pretty loud, actually. All right, the next problem is about the Doppler effect. So I pulled this one up here on Wikipedia, and here in this little animation, maybe you can see that. So as the car is going there, as wherever you're gonna go towards, the wavelengths get shorter, which means the frequency gets higher, and you're moving away from something, the wavelength gets longer and the frequency gets higher. This one here would be the general equation. I'm going to show you this in just a moment. By the way, on Wikipedia they use C here for the propagation speed of waves in the medium. I use VSOS for the speed of sound, and I'm also going to put the FO in the front. I'm going to call it frequency of the source, and then this one here is going to be the frequency of the observer. And notice the plus minus and the plus minus. I actually changed this one here to a minus plus, and I think the openstax textbook does that too. So here's the equation. When I write it down, it looks really similar, yet I do have a couple of differences in there. So you see here the observer's frequency. Here's the source frequency on the other side, and then I have a numerator and the denominator, and both have in common that here is the speed of sound. There we go. And then the difference is that this is the observer's velocity, and of course if the observer is at rest, then that means that is a 0 right there, so nothing happens there. This one here is the source velocity in the denominator, and again, if the source is actually not the one moving, then that is actually a 0 here. Okay, why the plus minus and the minus plus? Okay, the plus in the numerator means that the observer is moving toward the source, at which point you get a higher frequency over here. Well, you get that when you have a plus right there. And when the observer is moving away, you get a smaller frequency. Well, you get that when you have a minus in front. So the plus, the top one here, the plus is for moving toward, and the minus is moving away. The same thing happens with this minus plus here. The minus is moving toward, and the plus is moving away. So watch what happens. Or now listen carefully. If the source that is moving toward the observer, then of course the frequency gets higher, and therefore I would have to subtract, because then I make my denominator smaller, and therefore my overall fraction gets larger, and yeah, I have a larger frequency. And if the source is moving away, well, then I'm going to apply the bottom part of that, which is plus. So I add the source velocity to the speed of sound, which makes my denominator larger. Hence, my overall fraction gets smaller, and my observer's frequency gets smaller because the source is moving away from that. So that's why I have the plus minus and the minus plus. So the top of each one of them actually means toward. The bottom of each one of them means away. And that depends on, is it the observer that's moving or is it the source that's moving? Okay, so let's finally do this problem here. What frequency is received by a person watching an oncoming ambulance moving at 110 kilometers per hour and emitting a steady 800 hertz sound from its siren? The speed of sound is 345. What frequency does she receive after the ambulance has passed? So I have to do this twice. Let's see. So here, oh yeah, actually here I meant to plug in the number already. So that's actually 800 hertz right there. Sounds like 1 sig fig, but you know, we're gonna drag it out to 3 sig fig. I wish they wouldn't do that in books. They, you know, let's do 2 sig fig because of this one here. I wish they wouldn't do that here. They would give us other numbers here, but oh well. So 800, and I'm gonna have a 345. It says by a person watching an oncoming ambulance moving, so plus minus 0. There is no the observer is not moving, the source is moving. So the ambulance is moving toward the observer, so I'm going to have a 345 and apply the top one because it says toward, so that minus there. And then I cannot plug in 110, I have to convert that to meters per second, so I divide by 3.6 and I come up with 30.55 repeating, so 30.56 is what I'm going to do there. And converting from kilometers per hour to meters per second is you divide by, no, you multiply by 1,000 and then divide by 3,600, so overall I divided by 3.6. And so I'm going to have, let's see, I actually did this earlier just to make sure I'm on the right track here. So all that here, when I plug this into the calculator, I have to make sure I put parentheses on the denominator so that it divides by the whole thing here. And I'm going to come up with 878 rounded. I'm going to call it 880. Yeah, as the answer with the 110, you know, 2 sig fig. So 880. And then the unit is hertz, because in the fraction we have speeds divided by speeds, so all those units can divide out, and I have the frequency here, simply the hertz stays alive. All right, gonna do this second time. I would give myself a break here, but I think I can do that actually a second time around, because the only thing that changes here is what frequency does she receive after the ambulance has passed, which means it's basically the same equation. The observer is still at rest, 0, but now the source is driving away, so I'm going to take the bottom part of that negative plus there, minus plus there in the denominator, and so I add that, and I'm going to come up with, let's see, 735 rounded, well, actually 730 rounded to sig fig. There we go. Whoops. All right, and yeah, it makes sense as I applied the minus plus here in the denominator. The first one has to be a higher frequency. The ambulance is moving toward the observer, and this one has to be a lower frequency. The ambulance is moving away from the observer. All right, and I think this is the last one that I want to do. So this is about the flute. So I looked it up, and this one here, I know it says recorder, and as a German, that's kind of a strange word, and I looked at where the name is coming from, because what you see there in front, that's to me a Flöte, which translates obviously as flute. So here's the name and the etymology for it and so on, and in fact at some point it actually says right there flute douce, which is apparently a French word. That's where that comes from, and in German we adopted the word Flöte for that, what you saw there. And this one here in German we call it Querflöte, because quer means diagonal or to the side, and that of course is the one that in English you call a flute, and you see this person here respectively. I think I found it here right there. So this is actually the flute we're looking at. By the way, look at the length of this one here. So this is in German Querflöte, or to Americans simply the flute that you use in an orchestra. Notice how long it is. Looks like about 2 feet, and you will see what we're going to get here in a few minutes for the answer. Okay, so let's do this one here on the flute. How long must the flute be in order to have a fundamental frequency of 262 Hertz? This frequency corresponds to the middle C on the evenly tempered chromatic scale. On a day when air temperature is 20.0 degrees Celsius, it is open at both ends. Okay, they tell us, hey, we don't have the normal 345 meters per second that they usually give us in the OpenStax textbook for the speed of sound, but it's going to be slightly different, so at 20 degrees Celsius. So we have to compute that first, and this one is the equation for determining the speed of sound. So it's 331 times the square root of what the temperature is in kelvins divided by 273. The 331 applies when you actually do have 273 kelvins. So if I plug that in, this would be 0 degrees Celsius or 32 Fahrenheit. Notice I'm simply going to get the square root of 1, which is 1, and I would get 331. So that's the speed of sound at 0 degrees Celsius at the freezing temperature. Well, that's not what we have. We have 293 kelvins, 20 degrees Celsius. And when I plug that onto my calculator, I'm going to come up with the following. So 331 times the square root of 293 divided by 273, parentheses, enter 342.9. I will call it 3 sig fig, 343 meters per second. The kelvins inside the square root divided out, and right here, kelvins divided by kelvins, and what survives is the meters per second right there. So that's the first thing we're supposed to figure out. I'm going to prep the second part. All right, I think I prepped the second part. So that one is the equation for an instrument, a tube that is open at both ends, and if it's closed at one end, or if it's closed on both ends, or if you have a string, which also would be like a tube that is closed on both ends, then that particular equation that we have here would look different. So here we have the frequency. The n here means the number of harmonics or the number of overtones. So for harmonics, n equals 1, that's the first harmonic, which is also the overtone, which is also the fundamental. 2, n equals 2 is the second harmonic, which is also the first overtone. N equals 3 is the third harmonic, which is also the second overtone. Get a little confused there, right, between overtone and harmonics. I guess these are musical terms. So that one is then the number of the harmonic or the overtone times the speed of sound divided by 2 times the length of the tube. So I'm going to plug in numbers. It asks for the fundamental, so the n simply is a 1 right there. And then I'm going to here plug in, let's see, I just calculated this one here, 343, and then I have 2 times, and now I made a mistake because it's not asking for L, it's asking for F, so I have to do an algebra step, and Okay, and I'm back as I try to fix this one here.
So actually, I shouldn't type anything in here because I'm actually supposed to figure out what the capital L is. So I have to do a little bit of algebra, but it's no big deal because I just have to swap the length with the frequency, which I did right here. There we go. Swap the length with the frequency. Turns out I still plug in the 1 and the 343 and the 2 is there, and here's the frequency, which is 262. There we go. And this one here, by the way, I don't need because, as I said, I did have to do the algebra step first. Okay, gonna go back in here, equals, and so I'm gonna have 343 divided by 2 and divided by 262. So I'm gonna come up with 0.6, let's see, 3 sig fig, so 0.655. 0.655. The units are meters per second divided by Hertz, which is per second. So the per second divides out, and the meters remain. So I'm going to have 0.655 meters, which is 65.5 centimeters, which is a little bit over 2 feet. And you saw the person earlier playing the, what I call the Querflöte, the typical orchestra flute, and that indeed looked like 2 feet long. So they can still play the middle C on that one. They wouldn't be able to play any note that is lower than that, because that then would actually require a longer tube so that you can actually fit the wavelength or the half wavelength in there, because otherwise it's just not going to work. All right, and that's it. And yeah, as I said before, I'm not doing all the problems. I'm just going to do a number of them.